And I'm going to tell you a bit about some joint work with Mustafa Fall from Senegal and Ignace Minland, who is in Cameroon at the University of Douala. And this is about a problem connecting the geometry of an asymptotically flat end and some potential theory. So here's a brief table of contents. I have an introduction where I'll set the stage of what I'm talking about. I'll give you an introduction to asymptotically flat ends of Riemannian manifolds and some of the ways one can try to describe these objects. I'll tell you a bit about capacity, and the heart of the proof really involves the Dirichlet-Neumann operator, so we'll talk a little bit about that, and then I'll sketch completing the proof. Okay, so to begin, a Riemannian manifold of dimension at least 3 has an asymptotically flat end if you can parameterize the complement of a compact set by the complement of a ball in Euclidean space. And with respect to this parameterization in these induced coordinates, the metric looks like the Euclidean metric up to these orders. So the difference between the natural metric that M carries and the Euclidean metric is something that decays, like order length of x to the minus tau. Derivatives also decay. So here's maybe a picture of something. You have a region, a compact region in here, which might have some topology or might not. And then outside of a large ball, you have something that looks like it's, as you go out towards infinity, it's becoming ever and ever flatter. So of course it's possible to, one thing I want to mention is that many applications also require some sort of hypothesis, some sort of decay hypothesis on the scalar curvature. A frequent one is, for instance, that your scalar curvature is an L1 function. So it's possible, of course, to have a manifold with several ends, and some of them may be asymptotically flat, or maybe all of them. Then you may have other types of structures at infinity, but we're going to only talk about one asymptotically flat end today. So a rough statement of our theorem is that if the end is asymptotically flat of at least this order, and this is actually a very fast decay. This tells you that the rate of decay of the metric to the Euclidean metric, the flat metric, is very, very fast. Then one can find a foliation of this end. And you should think of this foliation as basically, this foliation is going to end up being perturbations of large spheres. You can find a foliation of this end by surfaces, and all of these surfaces admit solutions to a certain overdetermined boundary value problem. And this, the fact that they admit these solutions to this overdetermined boundary value problem means that they are critical points of the capacity functional. So I'm going to have a precise statement of this later, but this is a rough idea of where we're headed. Okay, so I want to begin with just some background of asymptotically flat manifolds, what they are, why people might be interested in them, and what tools one might use to study them. So in general relativity, one often can use an asymptotically flat manifold as a model for a space-like slice of space-time. And there are physical reasons for why that might be a reasonable thing to ask for. And from this point of view, one of the goals of geometric relativity in particular is to try to extract information about the global geometry of your manifold from the structure at infinity. You might want to, all right, we'll get to some theorems of this in a minute. The first attempt at this was something called the ADM mass. This was introduced by Arnolds de Witt and Misner in sometime in the 1960s, I think. And it's basically an average of derivatives of the metric over large coordinate spheres. Now, on the face of this, this looks a little bit random because this looks like it depends very heavily on your choice of these coordinates. So remember, I had a choice of some diffeomorphism here. And you might think, well, I could choose some different diffeomorphism. I could just rescale this diffeomorphism. I could translate it. I can do all sorts of things. And why is something like this ADM mass even well-defined? So there's a theorem of Robert Bartnik from sometime in the 1980s, which says that actually if your decay is fast enough, if your rate of decay is at least n minus 2 over 2, then this ADM mass is independent of which coordinate choice you make. And your first example of these types of theorems I'm talking about is the positive mass theorem. And this is due to Rick Shane and Xingtung Yao. What did they show? They showed that when the dimension of the manifold is between 3 and 7 and the scalar curvature is greater than or equal to 0, then the mass is greater than or equal to 0. Equality can only occur in the flat case. So this is a very strong statement. And then there's been a lot of work on defining other notions of mass and trying to explore what kind of information mass gives you about the system in general. But unfortunately, this notion of an ADM mass and many other masses you find in relativity are not very well, they're not stable under perturbations. So fairly recently, Jeff Jaggery, Dan Lee, and Christina Sormani have produced a number of examples of sequences of metrics which converge in some sense. They converge, in particular in the Gromov-Hausdorff sense. They actually converge in a stronger sense known as with respect to something called the intrinsic flat metric. So they show that this ADM mass is lower semi-continuous, but can actually jump down. The value of the ADM mass can have a discontinuity. So in some sense, this is, if you want to think about physical models, this is not great because whatever physical model you would be using, you would want it to be preserved. You want it to be somewhat stable you want it to be continuous with respect to small perturbations of your space-time. So a parallel program tries to foliate an asymptotically flat end by some certain hypersurfaces. So I'll draw a picture of that. Here I have, again, this is my picture of my manifold with an asymptotically flat end. So you can think of, you just draw a bunch of these concentric rings. Now, you have to be a little bit careful about how you do this because you can imagine that these rings become more and more eccentric, that one side of the ring grows much faster than the other side. So you want to do this in a way that you have some control. So a model for this is a theorem of Huisken and Yao from, I think, 1995. And what do they show? They show that when the dimension of the manifold is 3, the ADM mass is positive, that one can foliate the end by constant mean curvature spheres. And their theorem is actually much more robust. They show that this foliation is unique, and that as the radii of the spheres goes to infinity, the centers converge. So the spheres don't wobble all over the place. But and since then, there's been a number of generalizations. You can generalize some of their work to higher dimensions in certain cases. You can foliate with other kinds of surfaces, umbilic surfaces, isoperimetric surfaces, Willmore surfaces, and so on. There's a large collection of papers related to this. Carla Cederbaum has a number of results in this direction. She has some joint work with Christopher Netz, for instance, showing that this wobbling centers behavior I was describing can actually happen if you weaken some of the hypotheses in the Huiskin-Yao paper, that the centers can actually diverge to infinity, that the foliation can actually be very badly behaved, and you might lack uniqueness. Eichmer and Chudosh construct a foliation of an asymptotically flat end by isoperimetric surfaces. And King and Tian construct foliations of other manifolds of asymptotically hyperbolic ends by constant mean curvature surfaces. Metzger and Lamb construct a foliation of an end by Willmore surfaces, and I think that work is only valid for dimension 3. There's a number of others who are working on this as well. So this list is not meant to be complete. Right. But one of the issues that people are discovering is that actually these notions of mass and a foliation of an end and so on, which depend on notions like volume and area, are very easy to destroy. They're very easy to make discontinuous under small perturbations. So with that, many people, I won't say many, but some people have started to look at other notions of a mass that one can try to associate, other functionals one can try to associate to a set which might be a little bit more robust, which might not behave so badly under perturbations. So some people have put forward this notion of capacity. So I want to give you a brief introduction to, there's a huge literature attached to this notion of capacity. And I'm going to touch on some of it. So how should you think of capacity? You should think of having a charge of 1 inside this region in omega 1 and a charge of 0 outside this region omega 2. And this difference in the charge from 1 to 0 in this shaded region here, this omega 2 minus omega 1 that I've drawn, this will induce some change in electrostatic potential between the inner surface and the outer surface. And this is exactly what capacity measures. If you want to formulate this mathematically, you can write it this way. So you have a normalizing constant here, and you take an infimum over the Dirichlet energy of all functions, which are 1 on the inner boundary and 0 on the outer boundary. And there's a picture. Then if you write down what that is variationally, you basically do a Euler-Lagrange computation. You find that there's a function realizing this infimum, and that function realizing this infimum will satisfy, well, it'll be a harmonic function. It will have boundary values 1 on the inner boundary and 0 on the outer boundary. And then the fact that this is this capacity is realizing the drop in electrostatic potential is really just the Gauss divergence theorem coupled with the laws of electrodynamics. Now, we were talking about capacity of a compact set. So how can I make sense of this? Because I know I have 2 sets. The idea is that now you want to make this omega-2 set very large. So you want to imagine this omega-2 to be a sequence of ever-growing, of increasing balls. So I can make that more formal by saying that this capacity of a compact set K is the limit as K goes to infinity of the relative capacity of K with a ball of radius r centered at some fixed point. Now, this limit exists because from my definition of the relative capacity, this is a decreasing sequence here. So I do actually obtain some reasonable limit, and I can write that reasonable limit as the infimum of the Dirichlet energy of functions over all sets which are 1 on the compact set. And then what I haven't written here is that I should satisfy some sort of decay condition, and it will actually suffice to take my function u in to have 1 weak derivative in L2. That will be a sufficient decay condition. And then once again, I do my Euler-Lagrange computation. Oh, and that's a typo. That should be, I have a function defined in the complement of my compact set, which is harmonic in the complement of K. The boundary value should be 1, not 0. Sorry about that. And the lim sup as x goes to infinity should be 0. So you should think of that as really a boundary value at infinity. Okay. So this is the functional I'm dealing with. And I want to remark that this functional is not completely coming out of left field. There are other people who have tried to incorporate capacity to geometric relativity. And for instance, Hubert Gray proved, this is in, he proved this along the way to proving the Riemannian-Penrose conjecture. So he found that this was, the Penrose conjecture is, you should think of it as a generalization of the positive mass theorem. But anyways, his theorem says that if you have a 3-dimensional manifold with 1 asymptotically flat end, and the boundary is minimal, then the capacity is greater than or equal to the ADM mass. And later on, he proved a generalization of this with Pengzhi Mao, where the boundary component is not necessarily minimal, and then you get an additional term here, which is basically the boundary integral of the norm of the mean curvature vector. There is a notion of a mass based on capacity, and you can formulate it this way. And what you're basically looking at here is, so let's talk through this definition here. I'm taking a supremum over something, and the supremum I'm taking is over all compact exhaustion. So my KJ is going to be a sequence of compact sets such that the union of all these compact sets is the entire manifold. And I want to take a supremum over all such sequences of compact sets whose union is the entire manifold. And once I have that, I take the lim sup as j goes to infinity of this quantity. And this looks a little bit funny, but this is basically what I have inside these parentheses here would be 0 in the Euclidean case if my kj's were a sequence of concentric balls. Actually, so this quantity in here is 0 for a ball. Okay, and then very recently, I think this was from earlier this year, Jeff Jaggery proved that this capacitory notion of mass is always greater than or equal to the ADM mass. And if you have enough decay, the two notions of mass agree. Okay, so given that we have this nice functional, I can try to minimize it. I can try to find compact sets K which minimize my functional. And on the face of this, so if I look at my definition of this capacity, if I think of scaling my set K, this is going to scale my capacity. So if I scale my set K, say by a factor of capital lambda, I'm going to scale the capacity by lambda to the power n minus 2. So I need to do away with that scaling factor. And the way I do that is I multiply by volume to the 2 minus n over n. So this is now a scale invariant functional, and I can try to minimize that functional. And I'm going to call a compact set or its boundary of this functional, I'm going to call that a critical capacitor. If it's a critical point of this functional. And these critical capacitors all admit solutions to the following overdetermined boundary value problem. So the overdeterminedness part comes from the fact that I'm prescribing both the Dirichlet data and the Neumann data. The Dirichlet data has to be 1, the Neumann data has to be constant. So most boundaries will, most compact sets K, or the complement of most compact sets K, will not admit a solution to a problem like this. Okay, so we can finally state the theorem. What do we suppose? We suppose that the form of my metric looks like this. I want to have 1 plus something that looks like r to the power 1 minus n times the Euclidean metric plus something that decays, and this thing that's going to decay is going to decay like length of x to the minus n. Derivatives are going to decay accordingly. And then in this case, I can find a foliation of infinity. This is indexed by, so there exists a rho naught and compact sets K rho indexed by rho greater than rho naught, such that on the complement of each K rho, I get a solution to this particular overdetermined boundary value problem. I have a harmonic function with boundary values 1, with constant, with the appropriate decay to infinity, and with constant normal derivative. And I can even work out what that constant is. It's this thing here. So we'll see later on that there's not much choice. There's only one possible constant you can have here. Okay. The heart of the proof really will, you're about to see, the heart of the proof really will come down to inverting the Dirichlet to Neumann operator of my asymptotically flat metric. So to get there, we have to do a little bit of reformulation and introduce some parameters. But what I'm going to do in this section is reformulate the problem a little bit, introduce my parameters, and then explain how this is related to the Dirichlet-Neumann operator. And then at the end, we'll complete, well, I'll sketch the rest of the proof. Oh, maybe I should give you some remarks. So as we said here, I have very fast decay. And this decay is fast enough to ensure that the ADM mass of my asymptotically flat end is actually 0. But the other thing to notice here is that I have no hypothesis on scalar curvature. So the scalar curvature in all interesting cases will change sign. I see this as kind of a trade-off that you can prove the existence of these kinds of foliations with, I think, a little bit easier analysis if you assume very fast decay. But on the other hand, that is maybe less physically interesting because you're forcing yourself into this case where the ADM mass or other notions of mass might be 0. And if you want to weaken, if you want to assume less decay here, so we'll see later on that this amount of decay is actually, you cannot get away with less decay for the proof I'm going to present. If you want to have less decay here, you need to introduce additional hypotheses, and we expect that if you want to introduce less decay, you're going to need to introduce something like positive scalar curvature to have any chance of proving an analogous theorem. So let's reformulate this problem. The first thing I want to do is, instead of having to solve a sequence of problems on different sets, I want to actually solve PDEs on a fixed set. So I'm going to rescale my parameterization by this radius rho. I'm also going to introduce a small translation, and I'm going to think of perturbing the unit sphere. So perturbing the unit sphere is pretty natural. My large coordinate spheres in these asymptotically flat ends are, of course, not quite round. So if I want to solve an appropriate problem, I might imagine that I would have to perturb this by a small function. And the translation we're going to see has to do with the kernel of basically the kernel of a Dirichlet-Neumann operator. This is going to recover the missing parts from the kernel. Okay, so under this change of variables, my original problem I was trying to solve becomes, I want to find a harmonic function in this fixed set, the Euclidean space minus a unit ball. I want my boundary values to be 0. I want the lim sup to go to 0, and I want the normal derivative to be a constant. And to have my parameters all have the correct order, what I want to suppose is that the C2 alpha norm of my perturbation function is order rho to the minus n, and also that my translation is of size rho to the minus n. Okay, so as I was alluding to, the basic idea of the proof is that my metric is very close to being flat. So, and my coordinate spheres are very close to being round spheres. So in the special case where I have Euclidean space and I have a round coordinate sphere, I actually know the answer. My round spheres are critical capacitors, and the function I would choose if I want to realize this capacity drop is exactly the Green's function. length of x to the power 2 minus n. So this is a nice harmonic decaying function as boundary value 1 on the unit sphere. And if I take the normal derivative with respect to the inner normal, I obtain this value of n minus 2. So I'm going to start by constructing an example. I'm going to start by constructing a solution which just looks like x to the power 2 minus n, but now I want to just perturb that x to the power 2 minus n by some arbitrary function on the unit sphere. And the next thing I want to do is I want to let psi, so this function v is not going to be harmonic. So what do I do to correct that? I choose a function such that the Laplacian of capital psi is minus the Laplacian of v, and I want, that should be an equal sign here. I want the boundary values of psi to be 1 minus v on my boundary. And I can write that 1 minus v as n minus 2 times my perturbation function plus some operator applied to w. And this operator is, well, it's a nonlinear operator. I'm not going to write it down explicitly, but the important thing is that it behaves quadratically in w. So with respect to any reasonable norm, it looks like length of w squared. Okay, so I've now constructed a nice harmonic function. It has the correct boundary values. It has the appropriate decay. What do I need to do? I need to choose, remember I have my parameters here. My parameters are the radius, w, and tau. I want to show that for every row, I can choose w and tau such that the normal derivative of this u hat is also constant. And this last step is equivalent to inverting the Dirichlet-Neumann operator. So let's talk a little bit about the Dirichlet-Neumann operator. So I've written the Dirichlet-Neumann operator down for the ball. And you can make sense of this for an arbitrary set. You can make sense of this for the Laplace operator, for other kinds of operators. But the idea is that I start with a function on the sphere and I obtain another function on the sphere. What do I do to get this other function on the sphere? I take the harmonic extension of my w, and then I take its normal derivative. And then actually I'm going to do something where I subtract off this, this value here. This looks a little bit funny, but the way to think about this is you know what the harmonics of the sphere are. The harmonics of the sphere are generated by harmonic polynomials, and the first harmonics are actually generated by the linear functions. So the normal derivative of my linear function restricted to the sphere is going to give me exactly this term. So that's why I have this other term added here. We'll see this come up later on as well. Okay, so it's well known that the spectrum of this Dirichlet-Neumann operator is exactly the non-negative integers, and the kernel is spanned by the restriction of linear functions to the unit sphere. Right. Okay. So how do we begin trying to show that we can choose our parameters correctly? So the first thing you have to do is write out the normal derivative of our test of our proposed solution. So remember, our solution looks like this guy plus some other piece that I have here, which is choosing to cancel out the bad terms that come from my original choice of v. So if I compute the normal derivative, I find my leading order term first I'm going to get this n minus 2, which is what I expect, and then I get this term, which comes from the leading order term in the metric. And the remaining terms I have, let's look at my remaining terms. So I have one term which comes from the translations, which you kind of expect. I have a term which comes from W. And then I have a quadratic term, and the other term I have here is the gradient with the inward unit, the inner product of the gradient of psi with the inward unit normal. Now, it turns out if you look at this expression for h closely, you'll see that the limit as rho goes to infinity of rho to the power n minus 1 times h exists, and that gives you a nice smooth function. So I'm going to look at this function. I'm going to compute Taylor expansions at infinity, and what I find is that the first thing that's interesting is that the derivative with respect to the w variable, the w component, is actually this Dirichlet-Neumann operator I had a couple of slides back. And the other thing is that the derivative with respect to the translation parameter is I have a normalizing constant here, but it's essentially sigma times an inner product with tau. So what do I do to complete my proof? So I'm going to choose a function which, so if I look at, basically, if I look at what I want to arrange here, I want the normal derivative of this to be constant. I move the non-constant stuff to the other side. And what I'm going to have is essentially this term sitting on the other side here. And what I want to arrange is that this g tilde is 0. And I show that I can choose tau for every row. I can choose tau and w to arrange that this g tilde is 0 by using the implicit function theorem. So the first thing I have to verify is that actually when I take a limit as rho goes to infinity, I obtain the correct value. That the limit as rho goes to infinity of g tilde of rho comma 0 comma 0 is actually 0. So that's the first thing I have to show. And then what do I do? Well, I project onto the first spherical harmonics and their orthogonal complement. And what I find is that by my expansion for, where did it go? My expansion here for this part, once I project that orthogonally to this first spherical harmonics, I obtain something that's an isomorphism. So I can invert that part. So what does that mean? That means that for any large rho and small tau, I can choose a w depending on rho and tau such that pi of this guy is equal to 0. And then on the other hand, the other part of my derivative shows that I can for any large rho and small w, I can choose a tau depending on rho and w such that the orthogonal projection is equal to 0. And when I put those two steps together, I arrive at my solution using the implicit function theorem. Okay, so I'm going to give you a couple of references. The paper I'm referencing, the paper this talk is based on, is on arXiv. So here's a reference for it. And the other paper I want to reference is this paper from earlier this year by Jeff Jaggery, where he talks about the relationship between capacity and volume and geometry and infinity of asymptotically flat manifolds. And that's all I have to say. Thank you for your attention.